Watch what happens when an autonomous system attempts to scale without the correct structural foundation. The complexity outpaces the constraints, and the system shatters. The technology industry frequently treats agentic AI as the inevitable next step in artificial intelligence, a simple, linear upgrade from current chat interfaces. System engineering suggests otherwise. AI consists of three distinct structural architectures, each built for a highly specific kind of work. This diagram illustrates the first structure, a predictive model. It pattern matches historical data and converts it directly into a single quantitative score or forecast. These models are fast and reliable, but they structurally break down when the world changes and new variables appear. To handle changing variables, we use the second structure, generative models. These sample from learned distributions to produce entirely new, open-ended content. That flexibility comes with strict limits. Generative outputs are structurally stateless, reactive, and prone to hallucinating facts. That brings us to the third structure, agentic AI. Instead of a single reaction, an agent sets a goal and runs a continuous loop, planning steps, using external tools, and observing results. This continuous feedback loop handles genuinely dynamic, complex workflows. This structural weight limits agentic AI to specialized workflows, governed by 6 severe constraints. To understand these constraints, we first have to look at the mathematics of multi-step execution. This graph plots success probability against the number of autonomous steps, visualizing the defining vulnerability of an agentic loop. A predictive or generative model calculates its error rate exactly once, making a single generation and then stopping. Let's assume an agentic model starts with a highly impressive 95% success rate for a single autonomous step. As the agent loops through a 20-step workflow, that 5% margin of error multiplies across every consecutive action. By step 20, that initial 95% reliability mathematically collapses to a 36% chance of success. It operates exactly like physical erosion. Each successive stage weakens the integrity of the previous one until the foundation gives way. This mathematical decay restricts the maximum viable length of any autonomous workflow that lacks an external human stepping in to correct the trajectory. In an enterprise environment, the vast majority of daily tasks lack irreducible complexity. They are linear, predictable processes. Forcing a simple workflow into an agentic framework purely to utilize newer technology introduces probabilistic decay where none existed. A 95% reliability rate on a single step is negated when the system architecture demands long chains of uncorrected autonomy. Mathematical probability is only the first constraint. Agentic models also face physical limitations when deployed into production environments. This split screen compares real-time perception to an iterative agentic loop. Agentic models are physically too slow for real-time decisions. They rely on sequential calls to language models, requiring complete cycles before moving forward. Waiting seconds for consecutive API responses creates bottlenecks for rapid classification tasks, like financial fraud detection, where decisions must occur in milliseconds. This latency disqualifies agentic architecture for physical hardware perception, such as processing sensor data in autonomous vehicles. In high-velocity environments, even a fraction of a second of hesitation is fatal. Reactions must be absolutely instantaneous. The second physical constraint is exponential token economics. This countertracks token consumption tied directly to an agentic loop. Operating costs scale linearly with the degree of autonomy granted to the agent, not task difficulty. Generating a single block of text has a fixed single-shot cost, but an agent continuously calls tools, observes outputs, and revises its plan, consuming tokens the entire time. This compounding operational overhead makes high-volume agentic deployment for routine tasks economically unviable. High-speed or high-volume deployment for agents directly violates the constraints of system physics and token economics. Operational frictions like speed and cost are secondary to the risks regarding system security and regulatory compliance. This diagram maps the critical boundary separating isolated computational environments from actions that alter the real-world state. Predictive scores and generative text artifacts exist safely inside isolated read-only bubbles. They observe data without touching the underlying systems. Agentic models are designed to cross that boundary. Their purpose is to execute dynamic actions and interact with external systems. When an action is autonomously executed outside a sandbox and in the real world, the impact is often entirely permanent. Because agents execute real actions, their structural failures are different in kind. They are strictly irreversible. The cost of failure shifts from a low-stakes error, like poorly written text, to a catastrophic failure, like incorrectly modifying a live production database. This irreversibility creates a massive compliance bottleneck in highly regulated industries, like finance and healthcare. This visualization shows an audit tool struggling to trace a path through a chaotic, multi-path logic tree. It demonstrates the difficulty of auditing a stochastic, autonomous reasoning process compared to linear logic. A deterministic predictive score is highly auditable. A specific set of inputs will yield the exact same output every time. An agent dynamically generates a multi-step plan using a large language model. That fluid, reactive process is difficult to reverse engineer for strict compliance reviews. When real-world stakes are irreversible and regulatory compliance is mandatory, the flexibility of an agent becomes a severe security liability. We can synthesize these 6 constraints: probability decay, latency, cost, task complexity, irreversibility, and auditability into a unified deployment framework. This is the deployment matrix. It defines exactly where each architecture belongs based on its specific engineering constraints. Predictive models belong firmly in the bottom left quadrant for tasks with low complexity and a low tolerance for latency. Generative models sit in the mid-complexity space, where isolated, stateless outputs are acceptable. Agentic models are locked exclusively into the top right quadrant, requiring both high complexity and high tolerance for computational cost. Agentic AI is built for one environment: workflows where genuine complexity makes multi-step planning unavoidable. If a system requires real-time execution, massive volume scaling, or bulletproof reliability, predictive or generative architectures remain structurally superior. System efficiency comes from precision, matching the exact architectural tool to the exact physical requirement of the task. The mark of a mature systems architect is not deploying the most autonomous artificial intelligence available. It is deploying the exact level of autonomy required, and absolutely no more.